focusing on suspended solids in the Yarkon River. And she did her first postdoc at our Department of Marine Geosciences at the University of Haifa, and second postdoc in hydrogeochemistry laboratory at Migal, Israel. And now she is a research associate at hydrogeochemistry laboratory at Migal, and a lecturer at the Department of Environmental Sciences at Tel Hai College in Migal. And her main research interests are soil water geochemistry, biogeochemistry, and isotopes.
Thank you. Okay, hello everyone. So the subject of our talk today is sediment and trace metals distribution in an urban winter pond, which is in Netanya, Israel, urbanization versus regional effects. And this research involved several experts from around the world, actually. Nadia Toch from the Israel Geology Institute, Noam Levin from the Geography Department of the Jerusalem University, Gail McKean, which is a mathematics professor from the Northern Kentucky University, Henko de Stickler, who is a geochronology and sedimentologist expert from Holland, and Revital Bookman, who is a sedimentologist from your department. And I've done this research under Revital's supervision here in this department, with close guidance from Nadia from the Geological Survey. Right. And why should we care about sediments and trace metals in urban ponds? Well, we are all the time exposed to metals emissions from natural and from polluting sources. And these may include toxic metals like lead and mercury. And in high levels, we are more exposed. And of course, we want to know how we were exposed, in which rates, and from which sources to limit that. And wetlands, ponds, all kinds of water bodies, and which hold sediments, may be great recorders for the pollution history and pollution present in many places, and in urban places it can be even better and stronger evidence. And we actually wanted to reconstruct the history and to learn about the sources. And in this research that I will show today, we used an interdisciplinary approach, which means integrating knowledge and methods from different disciplines using a real synthesis of approaches. And as I shown you, we combined different experts from different disciplines in order to solve this complicated and dynamic metal pollution history in a sedimentary environment controlled by anthropogenic activity. So, with the geochemistry, with metal concentrations and lead isotope, stable isotopes, geochronology with 210 lead age of sediments determination, history, including analysis of historical maps and historical emission records, mathematics, using a geochemical mixing model, sedimentary, of course, particle size distribution and organic matter content, and geography, which included the GIS analysis to reconstruct the watershed contour. And all this in order to understand those strange and complicated metal profiles. And I will just showing this as a glimpse at this point of the talk, just to show you how strange they are, how in different locations of the pond we got different profiles of the metals, and also different profiles of lead stable isotopes. And of course I will talk about it more profoundly later on. So we are talking about Dora winter pond in its geographical context. It is located in the heavily urbanized and developed coastal plain of Israel, specifically in Netanya, in the southern part of Netanya. And you can easily see the difference in the map, in the historical map from 1880 how this area was actually with no development, no buildings, of course. What we had in the coastal plains were many wetlands and sand dunes and Kurkar ridges, and actually our watershed is between two ridges of Kurkar, and also there is a big sand dune here at the south. And through the years, more and more construction along the coastline has limited all the water bodies. But our luck is that our little pond Dora kept intact, although its watershed went through many processes of development and construction. The pond itself, we suspect, was not interfered, was not disturbed, and we know this from the line of eucalyptus trees, which you will see better in this picture, which was already shown in ancient maps from the beginning of the 20th century. So going back to here, the Dora pond is actually a seasonal pond with winter and summer cycles. In the winter, throughout the summer actually, it is flooded, and there are many water vegetation. However, at the end of the summer, towards the autumn, the pond dries out and the vegetation wilts and drops to the ground, where it starts to degrade, but on the way it brings with it all the little particles from the atmosphere that it caught during the year when it was up and blooming. And this is a great way of dry depositing particles and having this pond, the ground of the pond, the sediment, a great recorder of particles in the atmosphere. Okay, so we had three main cores, which we collected from the north, the center, and the south margin of the pond. And you see there are 23 centimeters, the longest above 40 centimeters, and 25 centimeters at the south. And okay, we'll start to see how they look. So as for their sedimentary features, first let's see the particle size distribution in selected depths. I'll start with the center. You can see that from selected depths, the distribution looks very similar. I can tell you here is something around like, but it's exactly 100 micrometer size, and all of the particles are below 100 micrometers, whereas in the north and in the south, you have two populations of particles split at 100 micrometer. And if we look at the profiles, the full profile of the fraction of below 100 micrometer particles, that is the fine fraction in our sediment, we can see again, starting with the center of the pond, that it is totally homogenized. It is practically it is only fine particles of the same character, while at the north and at the south, we can see that at the upper levels, you get a very low fraction of fine particles. That means that it has a high fraction of coarse particles, specifically very easily noticeable as sand. And you can see here the fine particles buried below, and also here you can see that the profile starts with fine particles and then it changes to coarse particulates. Similarly, the organic matter, we distinguish between the fine organic matter and the coarse particulate organic matter. The sediments, as I will show you in a few slides, the northern and the southern had really a coarse particulate organic matter at the lower levels, and we had to separate them from the sediment itself. and then the little particles unseparable from the sediment were measured by 550 Celsius LOI digestion, loss on ignition digestion, if you're familiar with this method. So we distinguish between the two. So again, you can see that the center of the pond had very little coarse particulate matter at the top, which is very natural, and hardly any, actually negligible material throughout the profile, and the normal degradation profile. Whereas we see totally different story at the northern and at the southern margins. And talking about the total 210 lead activity, we will go to talk a few words about it. Okay, so this radioactive isotope is used for dating sediment because it is the total activity that is measured within the sediment, within each sediment layer, is composed of two sources. One is the background, called supported 210 lead, and one is the excess activity, the unsupported, which comes from the atmosphere and decays within the sediment, and it forms a total activity line of decay. And by modeling this trend, we can actually get the age of each layer. And with that, we get the age of the whole profile until the age of 150 years. Because of the half-time of 22.3 years of this isotope, the maximum we can get is 150 years of age of sediment. Below that, we just get the supported background values, which cannot tell us anything else. So going back to our profiles, you can see here again, like I shown you, the profile, the natural trend of decay of the 210 PB. This is very similar to what we find in the DR5 sediment, but the DR7 shows generally the same trend of decay, but you can see that where we don't expect any more activity, we did get some activities telling us that something has changed, something has disturbed the normal decay trend. Okay, so just giving you some feeling about how those cores look like. The northern core was composed of sequences of sand and dark clay at the upper part, while the lower part was composed of very dark and fine grains and lots of organic matter, as I told you, and I want to show you how they look like. So you can actually recognize, I hope that it's clear enough, you can actually recognize the particulate matter that was just buried down below here, above all the deposited, newly deposited material, and you can also see some measures of metals with really high levels in the sediment and in the organic matter itself also. So from all that I've shown you till now, we can all get the feeling that the DR5 core from the center of the pond was in the most quiet depositing environment with less disturbances, and we trusted that sediment core to give us the history, the pollution history of the area, and we researched into that. A few words of each parameter about the lead concentrations. We are focusing in this research on lead, but giving more information about all the other trace metals which we tested. So we measured the leach and the total. The leach means that it was extracted with a diluted acid solution, and the total means that we determined the levels, the concentrations, after a very harsh, very strong digestion of the sediment. And you can see that there is looking from the bottom, there are very low concentrations at the bottom, rising a bit, being very constant for a long time, and then starting to rise around 12 centimeters from the top, depth 12 centimeters, rising, peaking at a depth of between 2 to 3 centimeters, and then going back again. As for the isotopic ratios, let's talk about it for a minute, get to know it. So we have 4 major stable isotopes of lead, and we can use the ratio among them as identification for different sources, because different sources has different combination of those stable isotopes, and this can give us familiarity with natural and with polluting anthropogenic sources. And you can see that here also there is a very constant line and stable line throughout the bottom layers until the same depth where concentration started to rise. Also, there is a strong shift in the isotopes ratios, and it started to decrease in values. If we want to learn about what that means, we should get to learn the sources, the different sources. So you can see here a good example of lead stable isotopes ratios, potential sources and Dora samples in this diagram of isotopes ratios, different ratios, and you can see that there are 2 major lines, right? There is the line of the natural sources, which is based on the soils, natural soils from Israel, local soils, and Saharan dust, which is recognized as a natural source of PB to Israel, to our area, and also the anthropogenic, the petrol mixing line between American petrol and European petrol. The American petrol was, the leaded American petrol was used in Israel until 1992. And after that, Israel changed to European, first leaded and then unleaded petrol, which has a very distinguished composition from the American petrol. So this gives us this change, very strong change in isotopic composition, give us a way to distinguish between petrol before 1992 and after 1992. This is a great tool for people that deal with geochemistry and pollution and sediments, which is what we are doing here. So DR5 core, from the center, you can see that part of its samples, I can tell you it's the bottom samples, were on the natural line, and then it moves to the anthropogenic petrol mixing line. And just a second. Okay, so we calculated the fluxes of the various metals, because this gives us the real input of metals into the sediment by eliminating the dilution effect of sedimentation. And after doing that, we could look specifically at the flux of lead into the sediment and compare it to sources, either regional source or local source. The regional source is actually the national source, the national petrol PB emissions to the atmosphere, and we formulated those values based on the records from the Statistical Survey of Israel, which gathers the information about petrol combustion. And we can, and the local source is from a car count in highway number 2, which is very close to the pond. I think it's around 1 kilometer from the center of the pond, or from the border of the pond. And you can see that the trend line of the flux in the sediment and of the national emissions is very similar, and that actually gave us the understanding that the core from the center of the pond is giving us the full history of the regional of the coastal line, and we reconstructed the pollution history from the ancient era, but focusing, of course, on the modern era. And this was published already 2 years ago in Environmental Science and Technology. And actually, I talked about this 2 years ago here when I finished, 2 or 3 years ago, when I finished this research. And here I want to use those profiles as a model case in order to compare them to what we see in the margins. And we actually wish that those profiles, this model case, will be in use in other sedimentary and geochemistry studies in Israel to compare how different things are in different locations, to learn of the different disturbances. So let's start with comparing the DR5 core from the center to DR7 from the south. In DR7 we could also do the dating, the 210 PB dating of the sediment, because we reached there the background levels, which implied we reached the supported activity. We couldn't do that in the northern sediment, so we have the dating only of the southern core. First you can see that the distribution of the age along the sediment layers is quite steady in the center, in DR5, whereas in DR7, in the southern margin, you get a very sharp change in the age of the sediment, while most of the sediment layers are younger than 1960. So there was a very slow deposition here, and then which accumulated material, and then a lot of material came on in recent years and filled up the profile that we finally collected. Another interesting thing is the accumulation rate. So you can see here that the highest, the major peak of DR5 was in the 70s, in the mid-70s, which is conforms to what we know about general pollution, particulate pollution in Israel and in the world in the 70s. While in the southern margin, you can see that the major peak is in the beginning of the 90s. That means that we have here another source that brought material, that brought pollution and material to the southern margin. And look, and let's try to, since we have the age of the sediment, let's try to see how the concentrations and the isotopic ratios of lead are adjusted to going with the history that we know. So we see that if we look at lead, and I can tell you that the other trace metals had very, very similar profile of very high concentrations at the middle of the profile. You can see that the age of those layers is between the end of the 50s to the early 80s. And what we already know, from what I've shown you a few slides ago, is that the peak in PB pollution was in 1982. Okay, just like the age, maybe I didn't mention that before, just like the age of the maximum flux of PB to the sediment in the center. So we know that the maximum pollution of the American petrol was in 1982, not in the 60s, not in the 70s, and not in the early 80s. So this cannot be chronological pollution. Also, regarding the isotopic ratios, you can see here that the values in these particular sediment layers is actually getting lower in composition. And again, we go back to the diagram of the isotope ratios to be reminded of the sources. And we can see here DR7 core samples, excluding one sample from the very bottom of the sediment profile, which was on the natural sources line and consistently also had a very low concentration of lead, meaning it was not polluted or pollution did not reach it. You can see the rest of the samples are on the mixing line and actually closer to the European petrol signature. So we actually understand that in layers which are of the age of until 83, we get pollution which is much younger, from the early 90s. And that means that something has changed here. You can compare the geochemical features to the sedimentological features and see that until here we had high fraction of fine particles, where it started to change to more coarse particles. And all this led us to understanding that the coarse particles, the sand particles that came and filled up the sediment layers above the fine particle layers allowed for more recent pollution to penetrate deep down into the fine particles area, where there were lots of clays, lots of organic matter, as I've shown you before, the DOC, the dissolved organic matter, and sorry, not DOC, but the fine organic matter and the coarse organic matter, which are all great agents for sequestering metals and stopping their mobility, while the sand allows quite a good leaching of solutions carrying metals. So to confirm or reject this idea, we used a mathematical mixing model, geochemical mixing model, to learn of the composition, the fractions of the various sources of lead in each sediment layer. And this is based on the isotope ratios and about the concentrations, but in this case more on the isotope ratios. So you can see that the European unleaded and leaded petrols actually govern most of the layers of DR7, and we can see that the unleaded can be found more in the more recent layers, and that makes sense. While the American petrol, which was used before 1992, it was responsible for greater pollution in the atmosphere of Israel, as we could see in the core from the center of the pond. But in the southern core, we see more minor appearance of this American petrol, but at least we can find it in the sediment layers where there was this pollution of this American petrol. However, more interesting is to look at the leaded European petrol, which was used after 92, around this time, but migrated. That's what we assume and believe. Migrated down to the lower layers to be sequestered, as I said, by the other more stronger layers or constituents of the sediments. So to understand this behavior, we try to look in not only to the sediment, but to understand the context in the watershed. And we had analysis, GIS analysis of the watershed based on, first of all, to reconstruct the watershed contours. Noam Levin from the Geographical Department of the Hebrew University used all kinds of topographical maps to build the contours, the feature of the watershed itself. And you can see two lines. The light blue is the calculated watershed directly, but the dark blue gives the edited watershed contour. And we needed to edit this calculated contour because of the surrounding. We had to compromise on the surrounding. Why is that? In the yellow dots, you can see, we're going to find it around here, the area where the active sand dunes used to be. You can somehow see it here, right? And we know that sand dunes, which are composed, active sand dunes, which are composed mainly or strictly on sand, will just let the rainwater drip down and will not formulate, will not cause for runoffs, which will lead for water and material flow into the pond. So as long as this area was of sand dunes, it cannot be really considered as a practical part of the watershed. But once construction started, and you can see it it's the 70s. Once it started, there is disturbance in this area, and it is no longer an active sand dune which lets water penetrate, and it may result in runoff and material transport. You can see that in the southern margin, it started outside of the watershed in the late 60s, and then it got closer to the watershed. And with time more and more, and you can see that at the end of the 80s, coming to the early 90s, there is really a big construction area really close to the pond, to the southern margin of the pond. On the other hand, from the northern part, construction started actually at the 50s. I don't think that you can see it really clearly here. But if you look at it more closely, you can see it started in the 50s and it continued all through the time to get a really heavily built neighborhood at the northern margin of the pond, at the northern part of the watershed. And these diagrams summarize all the urbanization processes in the watershed. You can see here the northern part with Nov Jaked, Agabim, Kiryat Nardal, and then Givat Irusim, which got really close to the southern margin. And now we can look at our parameters with comparing to the geography chronology, which we learned from the air photos and maps, and comparing to the geochronology. So if you look at the sediment accumulation rate, you see that the peaks that we saw before now has actually, geographical context. In the 1970s, as I showed you, the Kiryat Nordau was built to the south at the edge of the southern tip of the watershed, and later on Givat Irusim in the early 90s is actually recorded in maximum accumulation rate of sand at the southern margin that we sampled. And that gives you the connotation, the geographical connotation of what happened in the southern margin. And likewise, we try to interpret the northern profile. We don't have the dating of this profile because we couldn't perform the lead 210 dating, as I said before, but we can try to see if it works anyway, because we saw that in the 50s there was the beginning of the building operations, and we assume that this gave this mark of the high content of sand all of a sudden at the bottom of the sediment, but burying below it the fine particles and the organic particulates that I showed me before. And we assume that since then, in all the constructions of the the various neighborhoods, there were changes of material depositing and inputs of sands into the sediment, and this affected also the lead isotopes and the lead concentration. As you can see again, like we saw before for the southern core, we find high concentrations in the lower layers. Also, we find a very relatively low ratio at those layers. And I remind you that low ratios is a signature for us for the European, more recent petrol. And above it is actually petrol with or lead with signature of more ancient, not ancient, but older petrol, probably mostly American. Okay. And with that, we can get to understand the sequence of events in the pond margins, which consisted of urbanization, which led to sediment transport to the margins of the pond. Afterwards, after the sediment transport has begun, the more polluted area, at least of lead, took place. And this has led to metal redistribution within the sediment. And with this, I just want to thank the many people that helped in this study, the staff of the Geological Survey of Israel, the people from the laboratories, and the field people, Nimer from the sedimentology lab, it helped a lot. The people from the NEOS Institute for performing the 210 lead analysis, the people from the Hebrew University for the GIS analysis, and DRS Dora from the municipality of Netanya, which provided us with the maps of the watershed, which allowed us to perform the reconstruction of the watershed contours. The Ministry of National Infrastructure, Energy and Water Resources for funding this research, and the University of Haifa for funding me. That's it. Thank you.
Thank you very much, Iris. Any questions? Okay, so I have a question. So maybe I didn't understand. Is there any time-dependent tendency, or you just you describe the profiles at some specific moment, or you have records for for the additional years?
We have records for the sediment, and where we could perform the dating of the sediment, we can correlate the concentrations to the age of the sediment.
Yeah, I understand, but I mean that you took course,
Yeah.
for instance, at some time moment?
Yeah, only one time.
One time,
You don't need to
okay.
take again unless you sample only the very top of the sediment. Because as long as you do a good job, then your profile should be steady. No, excuse me, not exactly. The profile at the center, we expect to be steady. The profile at the margins are actually dynamic, because what started before continues. There is no reason why redistribution of the metals will not continue by having metals leaching down from the sandy part to the more fine-grained part of the sediment,
Okay.
and within this part also.
Okay. So I think that as it follows from the study with Revital and with Merav,
Yeah.
okay, it shouldn't be exactly constant from some depths, even from some depths.
Depends which material you have. If you have material which allows leaching of metals, I guess Merav did her research. Okay, Merav has it's totally different because she had her research in the Mediterranean Sea, right?
Yeah.
An area which I guess is more affected by turbulence or bioturbulence and movement of drifting of sands at the bottom, right? We are talking here about a very quiet pond, which we think this is the reason why it's such a great way to record pollution history.
Okay.
The difference is, I think, is here what controls the movement of metals. Perhaps we also had changes in the movement of metals. But here what controls the movement of metals is the grain size, coarse sand versus clay material, and the organic content of the sediment. At Murat's work, we were working, for people who don't know, we worked on Haifa Bay, and she was working on the shallow environment. So all the material was, almost all of it was coarse sand, and there the main control over the metal recycling or movement was the erosion of the or recycling at the bottom of the sea. So the controls are very, very different, although I think your model can work here also with different parameters, of course. It's a different environment.
A point that what was found, the sedimentary suspension, which is non-local transport, is very significant in the sea environment,
Yeah.
and it is
Here
true.
here there's no
Yeah.
suspension.
Yeah, but you have other processes like bioturbation.
I was very concerned about that. I was very concerned about many things in this research. And I talked with ecologists that studied this pond, and I tried to understand which kind of bioturbation might be here. And I got the understanding that I shouldn't expect too much bioturbation. And we just had, I don't expect that nothing will be formed there, but we had to be very cautious. And when we've analyzed the core from the center of the pond, we all the time compared the geochemical parameters to historical emissions, to what we know about pollution in this area of these different metals, and focusing on lead, as I said. And we found a very, very accurate profile. I didn't
Didn't
get
expect
into.
it to be so nice.
Yeah, it was too good to be true, but that's what it was. And I didn't get into details because I talked about it 2 years ago, 3 years ago here, and it wasn't the major thing in this talk. But that was a big concern, but we tried to solve this concern and trust our sediment finally.
Okay, the point that bioturbation, which usually just smooths your profile, so if you have just large gradients, it just works like smoothing, is a function of sedimentation rate. It can be approximated as some function. So if you have a large sedimentation rate, then if you have an oxygen, for instance, your bioturbation levels would be great, big, okay? So
Oxygen, is it?
if you have, the bioturbation, I mean that.
It's aerated sediment?
Yes, invisible
Okay.
sediment. So if you have a big sedimentation rate, then your bioturbation would also be significant. So
The
if you wish,
maximum,
we can talk about
okay,
that.
the maximum sedimentation rate in the center of the pond was in the 70s, while the very strong peak in fluxes of PP was in the sediment layer of the second part of the 80s, exactly when the maximum emissions of lead in Israel was at the same time. So again, I believe in sediment. I think we were really lucky to find that sediment profile, and this is why we actually hope it to be a good model case for other studies to compare for what was actually the fluxes of metals to this region.
Okay, other questions? Okay, thank you very much, Iris.
Thank you.